So we move over to lecture 18. Can you just see if it's working? We move over to lecture 18, and in the lecture 17, the one before, we were talking about fractional crystallization. We continue that discussion into this, and we try to conclude it. So we are in lecture 18 now. In the last class, I was talking to you about the fact that sometimes, equilibrium crystallization and equilibrium melting, in both of these processes, the crystal and the melt were in equilibrium, which means that there was exchange of matter across the interface between the crystal and the melt. No matter what, this communication is never lost. Now, from basic thermodynamics, it can be shown that at higher temperature, this exchange of matter through processes called intracrystalline diffusion, solid state diffusion, whatever it is, these processes are enhanced manifold. So at higher temperatures, because of the higher entropy of the system, there is a large amount of material transfer that is possible. As you cool down the temperature, what happens? The entropy decreases, and what happens? This exchange of matters becomes seriously impeded, and at below certain critical temperatures, they are completely stopped. So to increase higher temperatures is very important to attain equilibrium, if you might say so. In the last class, we talked about zoned crystals that form because of a crystallization process, where the early formed crystals were sort of separated, or their communication with the melt was impeded. This is what we were talking in the last class, that when you form a crystal, its exchange of matter with the melt is stopped. So essentially, the process is something like an equilibrium crystallization that is beheaded at different stages. So what you have is an early formed crystal is surrounded by another layer of a newly formed crystal and another layer of a newly formed crystal that all nucleate on an existing substrate, because it's easier for nucleation if there is a nucleating substrate, and it's more difficult to nucleate a separate crystal, although this is possible. Separate crystals, and we will talk to about it, it's a separate crystal. It's easier if you have an early crystal and the later crystals just nucleate on it. And nucleation of new crystals, it's possible, but it's much more rare. But we will show how that works. And we talked about zoning, that normally crystals that form at high temperature, or the core of the zoned crystals, the central part of the zoned crystals, do not show as much zoning as in the marginal parts. Why? Because the cores of the crystal that form at higher temperatures, there is more of exchange, and so homogeneity of the crystal is established, while as the temperature goes down, this exchange of matter between the crystal and the melt is impeded. We talked about a mineral called plagioclase before, and there we talked about that there is another problem, that the topology of the liquidus and solidus plays an immense role in forming zoned crystals. This we have discussed in the last lecture, and I won't elaborate on it. So we now know that zoned crystals are essentially indicative of crystal fractionation. Crystal fractionation means that the crystal is stopped from interacting with the melt. That is, the equilibrium is cut off. And this can happen due to several processes. It's not only that you have to physically remove the crystal. Even when the crystal is within the melt, that exchange of matter can be impeded because of lowering of diffusion rates, because of lowering of temperature, or because differences in the slopes, tiered slopes, temperature composition slopes of the solidus and the liquidus. Now, we can extend this a little further, and let me draw the diagram that I drew yesterday. So say, for example, here, where you have albite and anorthite, I gave you the compositions before, and the mineral here is plagioclase, as I told you. Mineral is plagioclase, which has the formula NaCa AlSi4O8, and this is made up of albite NaAlSi3O8 and CaAl2Si2O8. You can see here this 4 represents essentially Al2Si2 or AlSi3. So there are 4 of these sites, and Na and Ca replace each other in another particular crystal site in the plagioclase. And the diagram, I'm simplifying it, and the diagram is something like this, where this is temperature of melting of albite, and this is the temperature of melting of anorthite. Now, then what is the effect of this crystal fractionation? That is important, and this is, I will highlight, that what does crystal fractionation, we understand that crystal fractionation does happen, and so you get zone crystal. But what is the net effect of crystal fractionation? What does it do essentially? Why is it such an important process in crystallization and melting of igneous rocks? We talk of crystallization. Now let's say there is a melt of this composition. So this is 50, this is 25, this is 50, and this is 75. And on this direction, weight percent albite increases in this way. So let's say we have a melt composition which is positioned here, which is roughly at, you can see, albite 25. And once this melt composition, once the temperature reaches the solidus, then it will be there at a particular temperature. And if you extend the isotherm to the solidus, this will be the composition of L1, and this will be the composition S1. So you can see the crystal is enriched because this composition of the solid, so you can see L1 is albite 25 and S1 is albite, say, 5 here. Now this shows that the crystal that is crystallized from melt has higher anorthite content, which is the higher melting fraction that is enriched in the crystal. And as you remove anorthite, as you can see, when you remove albite from the system, then what happens? This melt changes into a different composition, T2, and here you have S2. And this is L2. So L2 would be somewhere around albite, say 30, and S2 will be albite, roughly say 10, let's say 10. Now the important thing is, imagine a situation where this crystal, say S1 or S2, let's take here, this is L2 and this is S2, yeah? This is S2 and this is L2. Now let's say by some mechanism, and we will talk about this mechanism, S2 crystals are physically removed from the melt. This is easier to understand, that is why I'm saying, let's say we move S2 out of the crystal melt equilibrium from the magma. So it's like you go to a shop and they are frying samosa in oil, and with a spoon they take the samosa out and they put the samosa outside, so you have the boiling oil. So here you can imagine the situation that happens, that you have the melt with the S2 crystals, and then somehow by some process the S2 crystals are just physically removed. Now what is happening here? Now the moment you do that, this L2 that is there now, it doesn't have any crystal. L2 does not have any crystal. So now this L2 becomes the new melt composition. The new melt composition. The new melt composition. If you remove the S2, then L2, which corresponds to the old L0 composition, remember this one was L0, this L0, which was the initial composition of the magma, and you separate S2 out of it, then the new composition of the magma becomes this. L2 now becomes the new magma composition. And you can ask me, so what? Yeah, that's the point. Say, for example, at this point, from fractional crystallization, we go back to equilibrium crystallization that I told you. Let's say, I will try to draw it in a different pen if possible. Say this was our initial L0, and is it right? So if this was the initial L0, if you see by earlier lectures, if you allowed equilibrium crystallization, that means crystals are not being separated. If you allow the equilibrium crystallization, then the last solid composition would have been here. The last solid composition would have been, the last solid composition would have been here, for which the liquid composite, the temperature would have been here. This would have been the last liquid composition, corresponding to which there would be, this would be the composition of the last solid, and this would be the composition of the last liquid at that temperature. Have you understood? If it were equilibrium crystallization, the black line. But now what we have happened? Now what we have done is, since we have separated the S2 crystals off from the system, this is your new L0. This is your new L0, new magma composition. So as if the magma starts to crystallize from the beginning. There were no crystals before. So now what happens? The solid composition now, if it was so for the equilibrium crystallization, this would be the crystallization. The final solid would be of this composition, and the liquid would be of this composition. So you see, from here, which would have been the composition of the last liquid, this would have been the composition of the last liquid if complete equilibrium crystallization was done. And now if you fractionate the crystals or separate the crystals, the point at which you separate, at that point the magma has changed its composition. And for that, if you now continue with equilibrium crystallization, this magma composition must move into here. So what has happened here is that the composition of the magma, the last magma composition, has changed from here to here, or even lower if you continuously fractionate it. Have you understood? If you continuously go on doing this fractionation process, then you will actually end up with a magma composition which is here, at the albite composition. You will precipitate pure albite. So what you're doing is, when you do the process of crystal fractionation with a physical process, what you essentially do is change the magma composition to a greater range. Your last magma composition becomes extended to lower and lower temperatures and lower albite content, higher and higher albite content. So your magma will become more sodium rich as you go on doing crystal fractionation. this process, this outcome, the process is called crystal fractionation. And the outcome of this crystal fractionation is what is called magma differentiation. Magma differentiation. Now, differentiation and fractionation, these are not synonymous terms. No. Fractionation is the process by which the crystal is not allowed to equilibrate with the magma. So this is the cause. And what happens? You have a differentiated magma. So this is the effect. So the difference between fractionation and differentiation is, fractionation is the mechanical process or the chemical process or whatever the process is of breaking the communication between the crystal and the melt, and differentiation is what results from it. So they have a cause-effect relationship. So this fractionation is cause and differentiation is the effect. What is the effect? That if you go on doing crystal fractionation, the magma composition becomes diverse and extended to more extreme compositions at lower temperatures. Have you understood it? So essentially, now, if from the phase diagram you go to a natural world, if you do equilibrium crystallization, then for equilibrium crystallization, you get a solid, homogeneous solid mineral that has the same composition of the magma. So you produce a rock. From one magma, you produce one rock. But when you induce crystal fractionation, then what you do is you can produce diverse rocks from one initial magma composition. That is the effect. So one magma composition in equilibrium crystallization produces one magma. In fractional crystallization, one composition of the magma produces multiple solid compositions. So you get multiple rocks from one magma composition. Now the Earth's surface is composed of diverse magmas. So if you had to say that these diverse magma each formed from one magma, unique magma, then you have to conceive of a mantle of the Earth, which is also very chemically diverse. But we know that the mantle is not so diverse. You know, mantle melting produces these metals. So, but we know that the mantle is not so diverse as is expected when we see the diverse rocks that are present on the crust. So essentially, this diversity of the rocks of the crust is not because the mantle is diverse in nature. No, the mantle is much, much less diverse. But because of crystal fractionation, the solids that it produced are mineralogically and chemically diverse. That is why is crystal fractionation, and we have the evidence like zone. I will give you some more examples of crystal fractionation. So crystal fractionation is the process by which mantle-derived magma, after all, most of the magma is derived from the mantle. So from the mantle that you produce this diverse magma, it undergoes one of the processes that causes the diversity is crystal fractionation. There are other causes. Everything you don't have to know in this very short introduction to earth sciences. Those who are petrology, your teacher next class would be able to amplify it more. But the important point to remember is crystal fractionation produces multiple solids and multiple magma compositions, as opposed to equilibrium crystallization that produces a unique solid from a unique belt. But you know, igneous rocks not only show minerals, not only show zoning, they also show a diverse kinds of textures, and that is important for us to understand how they do it. Diverse kinds of crystals, diverse kinds of textures that tell us a lot of things. Now, if we go back to equilibrium eutectic crystallization, I hope you have not forgotten the diagram already. So, eutectic crystallization, this is the famous diagram where you have crystals of A and B, pure, remember, and that you have temperature of melting of A and temperature of melting of B, and then you have so this is liquid, this is A plus liquid, remember A is pure, B plus liquid, remember B is pure, and A is pure. And this is the solidus, and these are the liquidus, and here you have A plus B. Remember, this is not AB solid solution. This is not AB solid solution. This is pure A and this is pure B, which means the rock is a mechanical mixture of A and B. When I write AB solid solution, it is A and B are two components of a solution in the solid state. Have you understood? So you cannot differentiate the two compositions. It's not a mechanical mixture, a chemical compound. Now, say for example, you start with a magma, you start with a belt having this composition. Let's say this is again 50, 25, 75, and you start with the magma composition. So you start with the magma composition, which is L0, and when the magma composition, when you cool or crystallization, then at this temperature, where the temperature is on the liquidus, A is in equilibrium with the liquid, crystals of pure A will separate out from the melt, and the melt would change its composition L2 and S2, and this is S1. Remember, the composition of S1 and S2, the composition of S1 and S2 is the same, but the composition of L1 and L2, they are very different. They are different, but the composition of the crystallized solid is the same. And they are pure S1 and pure S2. And if you remember, we divided it into this M and N, where M divided by M plus N, M divided by M plus N is the fraction of liquid, and N divided by M plus N is the fraction of the solid. And we also know from our earlier discussion that what will be the composition of the solid? Because this is a closed system, the eventual composition of the last solid will be this, and for which this will be the composition of the liquid at eutectic. We know this part. I have talked to you. If you have any questions, please, if you have any questions, you can write to me and I will post it. So I hope we can communicate that way. Now, let's take the situation where we have L2 and S2. Let us take the situation where we have L2 and S2 at temperature T2. So you can see here, fraction of the liquid is M divided by M plus N, fraction of liquid. and n divided by m plus n is the fraction of solid. So, at T2, L2, S2, this n divided by m is the fraction of the solid. Now see, at this point, if we had a camera, a stroboscopic camera, which takes a continuous photo of what is happening, what we will see? We will see the following. We will see these are, let's say, crystals of S2, and this is L2. These are crystals S2, and this is liquid L2. This is what we will see. What is the proportion of S2? Is n divided by m plus n should be the fraction of S2 in the total lift. Now at this point of time where the magma is below the Earth's surface and it's cooling, and this is the situation, let's say the magma gets a conduit through which it gushes out onto the surface of the Earth. What will you see? What will happen? If this gushes out very fast onto the Earth's surface and forms a lava flow, what will happen? What will happen is, the surface is at 25 degrees centigrade. Your magma temperature is 1000 degrees or something like that. So when this magma gushes out and falls on the Earth's surface, it will cool rapidly. When it cools rapidly, this is called, the word that is used, we have not done it ourselves, we have taken it from metallurgists. It's called quenching. When the magma is quenched, so when the whole thing is quenched, what we will see? We will see large crystals of S2 in a matrix. How will the matrix look? You see, the eruption of the magma was very fast and the cooling very rapid. So obviously, no crystals can form. So this would quench. L2 will quench as a glass. L2 will quench as a glass. So later after the eruptions, when I go and take a sample and cut it and see it in a microscope, I will see this occurring as crystals, which I can identify with a microscope, but this one is a quenched glass. There will be no crystals. And this texture is called porphyritic texture. Porphyritic texture. These are called, actually, these crystals are called porphyries. These crystals are called porphyries. When So what happens when the crystallization, when the crystallization is low? What does crystallization low means? When the fraction of liquid is high, that means the fraction of solid is small. Then what happens? When you nucleate a crystal, the crystal grows unhindered. Have you understood? Unhindered. So its surfaces grow into their normal shapes. All crystals don't have the same shape. Just like you and I, although there is a broad framework, we are not of the same shape. So similarly, crystals do not grow with the same shape. So some crystals, for example, grow as columns. Some crystals grow as a sphere. There are crystals which grows like this. Crystals can grow with different shapes. It depends on the mineralogy. You have been taught mineralogy, I understand. So we've been talking about mineralogy. from these crystals have different shape. So these shapes, when you cut, you will see different shapes of the crystals. But what is important is when you have this crystallization, when crystallization, the fraction of crystal is very small or small enough, where grain to grain contact has not been achieved. Grain to grain contact has not been achieved. That means a crystal can grow to its own shape and size. So grain to grain contact, when grain to grain contact is achieved, then what happens? The crystals cannot grow to their size because it is impeded by the surrounding matrix of crystals. So crystals don't grow to their full size. So what happens? There are three types of crystals. One is called euhedral crystals. Then you have anhedral crystals. And then you have subhedral crystals. These are the three terms used. Euhedral, subhedral, and anhedral. What is euhedral? It is something like this, as I drew. You see, all surfaces, very well developed surfaces. Very well developed surfaces. These are called euhedral phenocrysts. Euhedral phenocrysts. What is anhedral? Almost no shape. When you have anhedral crystals, it means that the crystal has not grown into its proper shape. Why? Because it was not allowed to grow. Why was it not allowed to grow? Because there was not enough space to grow. Why didn't have enough space to grow? Because there was a solid matrix around it. Solid crystal matrix around it. So this is why you have anhedral crystals. Or these are called anhedral phenocryst. Anhedral phenocryst. Or you can have this is subhedral, where parts of the faces are well developed, the other parts are not well developed. This also happens dominantly because parts of the crystal did not have enough space to grow, but there can be other methods. I will tell you in some times why subhedral crystals form. But dominantly, euhedral means when a crystal grows to its perfect shape and size. Anhedral is the other extreme, where we know that this is a crystal, but we also know that this is not its shape. It cannot grow to its full shape because there was not enough space to grow. And why didn't have space to grow? Because it was surrounded by a solid matrix of other crystals, and it did not give it the space to grow. And second is the subhedral crystal, which is intermediate between euhedral and anhedral, where part of the crystal faces have definitely grown very well, but the other parts have not grown so well. So these are some of the different types of crystals: euhedral, subhedral, anhedral. So here in this case, as you can see, when you have high volume fraction of the melt, and the crystal fraction is small, then the crystal can go to its big size, its perfect size and shape it can achieve. And then you get euhedral phenocrysts. Euhedral phenocrysts, these are called also porphyries, euhedral porphyries. And the texture overall is a porphyritic texture. It's a porphyritic texture. Sometimes, so this is what is called a porphyritic texture. Now, say for example here, let's say if this was a plagioclase crystal and it showed zoning, That means what? If it showed chemical zoning, that means the initial part of the magma before eruption on the Earth's surface, it underwent crystal fractionation. Have you understood? So in the initial part of the magma, when it was crystallizing slowly because it was at depth, why slowly? Because heat could not be dissipated very fast, because rocks, as I told you, are very bad conductors of heat and electricity. So the cooling has to be slow. But when, during that time, and if this crystals are zoned, that means there was crystal fractionation. But after that, the magma was erupted on the surface and had to cool rapidly. And so the rest of the melt did not have a chance to cool at all. And that is why they give you what is called a quenched magma or glass. And this overall texture is called a porphyritic texture. Sometimes there are other aspects of porphyritic texture, and I need to tell you that. Sometimes what happens, you see, say for example, this is the Earth's crust, and say a magma body is below and it is entering through a conduit. Say not very fast, but let's say it's slow. So if the magma is ascending in this direction, what will happen? The velocity of the magma, the velocity profile of the magma would be something like this. This would be the velocity profile of the magma. That means at the contact with the wall, which is a very bad conductor of heat, the magma will not move with the same velocity because of forces, that cohesive forces. It will not move fast. But the central part of the magma would move fast enough. So what happens? The velocity of the magma, the velocity vector of the magma is variable. The velocity vector of the magma is variable. So what happens if I draw this, if I blow this up now? So this is, say for example, so what happens when there is a magma flow? When there is a magma flow, say for example, this is where the magma flow, and this, for example, is a basement where there is no flow. No flow means the total vector is in this direction. Do you understand? There is no flow and these are faster flows. If we make things simple, then what happens? This is the direction of stretching. And 90 degrees to it is the direction of shortening. So this is the direction of shortening, and this is the direction of stretching. So now, say for example, if you have a magma, like say a matchbox or a cigarette packet, or say for example your mobile phone, if it had that shape and you're looking at a section, then the crystal, because this is the stretching direction and this is the shortening direction, what will happen? The mobile of yours or the cigarette packet of mine, it will align itself like this. So what will happen? Anisotropic crystals will be aligned in this orientation. Have you understood? So, if you take the magma, then the crystals are aligned so that the long axis is parallel to the stretching axis, and perpendicular to that would be the zone of flattening. So, crystals would be aligned in such an angle. Have you understood? If, for example, this one, Now these are called flow structures. Flow structures. These are very good features to show you in which direction magma moved. These are very good features to show in which direction the magma moved. So here in this case you will see this is also porphyritic texture, but there is a difference. What is the difference? Here you will get crystals like this, like a pack of cards. So this is called imbricate grains. This is called imbricate. Or it's called imbrications of euhedral touching grains. Imbrications of euhedral touching grains. That means this formed from magma, and because of a flow, they were all aligned like a pack of cards, like you shear them, and that's like a pack of cards. So this is one feature that you see in flow textures. Another thing that you see is like this. End to end touching euhedral phenocrysts. End to end touching euhedral phenocrysts. So these are two features that you will see. That the grains side on has imbrication grains, all euhedral in shape, and along the length you will have end to end touching grains. These are all indicative of magmatic flow textures. So this is a porphyritic texture, but with a difference. It's a porphyritic texture that shows flow structures. Have you understood? You can contrast this with such a texture. Let's say I will draw this texture. Say for example, a texture like this, where you have euhedral crystals that are randomly oriented, and they are clustered, and there is an aggregate of these phenocrysts. Have you understood? An aggregate of the phenocryst, where the phenocrysts are not aligned, they are randomly distributed. This means that the magma was not under any stress to flow. Have you understood? The magma was not flowing, or it was a static magma. But at the same time, why do you get this? Because of its forces that attract one over the other. It's very simple. It's very easy to see. When you put a bucket of water and you put a few grain husks